Okay, this is not an alternating series. The sign of 2n as n goes off to infinity is bouncing around. You know, it's certainly bounded above by 1 and bounded below by -1. It's just bouncing around all over the place. So what I do instead is I start to look at, you know, the absolute value of this over here. And I'm going to look for absolute convergence. So I'm going to write, I'm looking for absolute convergence, which is, it's a stronger statement, right? So I'm going to look for absolute convergence, And the way to do that is just look at this over here, n equals 1 to infinity, the absolute value. And if I could show that convergence, I'll say it converges absolutely. Well, kind of looking at this, I'm going to say this sort of compares with something that I kind of know about. And I'll write this one over here. I'm going to say it actually compares, because the sign's bounded above by 1. So I'm going to say it's, you know, n plus 3 to the n. And I'm going to say, you know, this is clearly the case over here. All right? Now, by the way, it's never going to get 1, but I'm going to play it safe by saying it can never be greater than 1. So this is certainly true. Then looking at this over here, I'm going to say, let's take a look. I'm going to say this over here, that this is, by the way, this is n equals 1 to infinity. By the way, this is a positive term series. Let's put this one over here. I'm going to say this one probably compares pretty well to 1 over 3 to the n. Boy, that's deja vu all over again, isn't it? And we've done that before. We've seen that. And that's certainly true for n greater than or equal to 1. Now, what do I know about this over here? This is convergent geometric series. What does that mean? This one's smaller than it. This one converges. And what about this one over here? It also converges. What kind of convergence are we getting? We're getting absolute convergence. So this is absolute convergence. Thank you.